Simplilearn. Your pace, your place.
Course: Cloud Computing Foundation. Introduction. Hello and welcome to the Cloud Computing Foundation course by Simplilearn. This course is designed for the participants who are looking at successfully completing the Foundation certification by EXIN on cloud computing. These slides contain all the basic materials required to prepare students for the EXIN Foundation Cloud Computing exam. Agenda. Let's now look at the agenda of this session. In this course, we will first be going through the introduction of cloud computing and how cloud is used, followed by the how cloud is implemented and supported. We will also look into managing and evaluation of cloud computing in this lesson. With this, we are done with the agenda of this lesson. Now let's go ahead and experience the session on cloud computing by Simplilearn. Introduction to cloud computing. All of us have heard of cloud computing and its benefits. We have heard of it as this new cutting-edge technology that is going to take the world by storm. We shall from here look at the concept of cloud, how it was conceived, and its uses. Objectives. In this course, we will be going through the basic concepts of the cloud computing platform, where we will be studying on what is a cloud, the technologies based on which cloud was evolved, how to build a cloud, design, deploy, and manage it. We will take a close look at technologies used before the cloud platform, their positives and shortcomings, and how due to these technologies, the concept of a cloud was conceived. We will see how evolvement in bandwidth and processing power has benefited us in our pursuit of cloud technology. We will examine the pros and cons of implementing a cloud platform, that is to say, situations that a company might have to go through if they decide to move to a cloud platform. Decisions they will have to make if they implement their own cloud infrastructure, and if they decide to take cloud as a service. We will be going through the different types of clouds. We will be analyzing the potential concerns an organization could encounter while moving over to a cloud environment. For example, potential security risks, legal issues, system availability, SLAs. We will learn about cloud computing standards and best practices as well. What you will have learned. At the end of this course, you will be able to identify the essential elements of what consists a cloud platform. You will have learned about various cloud platforms, information as service, IaaS, platform as a service, PaaS, software as a service, SaaS, etc. You will realize that we have been using some of these technologies in our daily lives regularly. You will understand migration paths for cloud adoption. You will be able to identify positives and negatives of shifting to a cloud environment. You will see how it is advantageous financially to move over onto a cloud platform and analyze which business processes benefit from this move. Along with the positives, you will be able to analyze the negative aspects as well, such as security concerns, legalities, uptime, SLAs, etc. You would have studied business cases where and why a company would want to shift onto a cloud environment, and the options they will have to implement a working model. You would have understood how to build a cloud network, technologies and softwares available to build, maintain, and sustain. You will be well rehearsed with virtualization architecture, stacks on how the architecture works, hardware required for virtualization functionality, etc. You'll be able to pinpoint privacy and security issues that companies should be concerned with and resolve before making a decision to move over to a cloud, identity management, federations and presence, and how mobility can be introduced in a cloud, mobile devices like tablets, laptops, smartphones, etc., cloud computing standards, and best practices. Overview. This diagram shows us the methodology of an effective working cloud environment. The most important thing to note is that all these factors are entirely codependent and have to work in tandem for us to have a functioning, reliable cloud platform. Please elaborate on the diagram. The NIST Cloud Definition Framework. This framework shows us the types of deployment models in a cloud. We can see there are 3 distinct models of deployment, and one can make a choice of which model to opt for. Private cloud. This is where an organization deploys their own cloud in their infrastructure. Instead of going for a regular network with physical computers, they buy virtualization-capable servers and virtualize most of their servers and client PCs, which they access by using thin clients. This also saves on a lot of infrastructure investments, and since the cloud is in-house, the security and total control still lies in the hands of the organization. This model is most suitable for large networks. Public cloud. This is where the organization opts to use the services provided by a third party. For example, Amazon EC2 or Microsoft Azure, and outsource their infrastructure. Here the control and security lies with the service provider. Community cloud. Let's say there are 4 organizations with almost the same computing needs. If they do an in-house infrastructure setting, each will have to develop its own network and maintain it, which is a costly proposition. Instead, they get together and pool their monetary resources and build a cloud which only these 4 organizations can utilize. It is not open to the public, so this is a community of people pooling their resources to develop their own cloud. Since there are multiple organizations using the same cloud, it cannot be called a private cloud, and since it is not open to the public, it is not a public cloud either. Then we come to the service models that can be used over the cloud. In the diagram, there are 3 major services listed. 1. Software as a Service, SaaS. This is where the software is located elsewhere at a remote location, and you can access it through the internet using a browser. The service here provided is that of the software, hence the app name. A simple example in this case would be your web-based email, Facebook, etc. 2. Platform as a Service, PaaS. Here, a design platform like .NET is rented for development purposes. Let's look at an example. You want to develop an application based on the .NET framework. Under normal circumstances, you buy a computer, buy the .NET framework for development, and also create an environment for testing the application. This is a lot of money. Instead, using your existing computer or a thin client, you approach Microsoft Azure and rent a virtual PC for the development, rent the .NET framework, and also rent the testing environment. Once you are finished with the application, you can just pay the rent for utilizing those services and discard them when done. This saves you from the initial infrastructure investment, and you only pay rent for usage. This also keeps the cost of your application down. Infrastructure as a Service, IaaS. This is where you rent computation and/or storage space as a metered service. This concept is based on utility computing, which has been around for years. However, utility computing never took off due to lack of virtualization, which made this model economically unviable. The cost in utility was approximately $1 for 1 hour of usage. This service is similar to a piped gas connection or an electricity connection. Let us now look at the essential characteristics of a cloud. On-demand self-service. This is a scalable model, which means you can upgrade or downgrade your infrastructure as needed yourself by logging into your account with the service provider. So if you feel that there is going to be a spike in the near future in your workload, then you can just deploy a few virtual machines in your infrastructure to manage the spike, and once the workload decreases, then you can discard those virtual machines. You will only pay for the usage of those virtual machines. Rapid elasticity. The upgrading or downgrading in this situation takes only minutes as existing templates are used. Thus, you do not have to wait for a long period of time for the machines to be deployed or destroyed. Resource pooling. All your hardware resources are pooled together to form a strong, reliable virtual environment to meet your needs. Measured service. The services provided are charged to you only for your usage and not on a monthly or a daily rental. If you use it for, say, just 5 hours today and 3 hours tomorrow, you'll be charged only for those 8 hours of utilization. Let us now look at the common characteristics. Massive scale. Clouds are generally deployed on a massive scale, that is, where the infrastructure is huge. This results in a lot of savings in infrastructure investment. Homogeneity. The infrastructure is composed of similar or identical parts or elements. Virtualization. This is a key component of cloud computing. Take out the virtualization from the cloud and you are looking at the grid computing model. More on this later in the workshop. Low-cost software. In a cloud, the emphasis is on using open source software to keep costs low. Also, licensing is entirely different in cloud for virtual machines. Resilient computing. When a virtual machine crashes, the ability to recover from the crash or deploy another machine for the same purpose is very quick. Thus, it can be said that it is resilient. Geographic distribution. Since the cloud works on the internet, it is possible for the network or parts of the network to be geographically in different locations and still be able to communicate with each other. Service orientation. The cloud model has been specially developed to deliver a variety of services to an organization or to your doorstep. Advanced security. If opting for a service provider, it is safe to assume that security will be taken care of, considering the fact that the provider's investment in security will be far more than that of a regular organization. It, however, bodes well to have those clauses covered in your SLA and to verify the factuality of those security measures. History of cloud computing. Here, we are going to explore the history of cloud computing. Most of us think that this is a brand new technology, recently introduced to the world, and everyone's trying to jump on the bandwagon. But nothing can be further from the truth. The concept itself was first introduced in the 1960s by J.C.R. Licklider, who was responsible for enabling the development of ARPANET in 1969. His idea was of an intergalactic computer network. His vision was to see everyone on the globe to be interconnected and accessing programs and data at any site from anywhere. It is a vision that sounds a lot like what we are calling cloud computing, says Margaret Lewis, Product Marketing Director at AMD. Other experts attribute the cloud concept to computer scientist John McCarthy, who proposed the idea of computation being delivered as public utility, similar to the service bureaus which date back to the 60s. Since then, cloud computing has evolved through a number of phases, which include grid and utility computing, application service provision, ASP, and Software as a Service, SaaS. We will learn about technologies like grid, utility, cluster, and virtualization that have helped us evolve into cloud computing. We will also be studying the data center architecture of grid, utility, and virtual machines. The development of cloud computing was stymied from the masses due to lack of bandwidth. However, since the 90s, the internet bandwidth has been steadily increasing, thus making cloud computing more available and beneficial to the people. One of the first milestones for cloud computing was the arrival of Salesforce.com in 1999. It was simply based on the concept of delivering enterprise applications through a simple website. Then came Amazon Web Services in 2002, which provided a number of cloud-based services. Then, in 2006, came the Elastic Cloud Compute from Amazon, offered as a commercial web service. Again, in 2009, Web 2.0 hit its stride, and companies like Google, Microsoft, etc. started offering browser-based enterprise application, Google Apps. How the masses benefit from these services is up to them. With a slew of these services being offered by multiple companies, and the technology still in its infancy, there are a lot of worries about legal issues, security, etc. We will be looking into these issues as well, and we'll be studying the Amazon Web Service, AWS, model as an example. History of cloud computing. Before the evolution of cloud technology, there were four major technologies. Cloud is essentially a repackaging of these four technologies, which translate into a much more robust and useful model. These four technologies are 1. Cluster computing, 2. Grid computing, 3. Utility computing, 4. Virtualization. These technologies have been around for decades and have been in use individually. We will be looking deeper into each of these technologies, and we will be able to understand that cloud computing is nothing but a culmination of these four. Individually, these technologies have had varied success ratios. A few were very popular during their time, however, due to their limitations, weren't able to sustain. As of today, hardly anyone uses these at all. 1. Cluster computing. A cluster is a set of loosely connected computers that work together so they look like they are a single system. The computers in a cluster are connected by LAN, with each computer running its own instance of an operating system. Clusters evolved due to the availability of low-cost microprocessors, high-speed networks, and software for high-performance distributed computing. The necessity for a cluster is to make a task or process highly available. Take, for instance, a task that requires a lot of computational power depending on the workload. The workload will spike any moment and drop at any moment. It would be a futile exercise to manually introduce systems when required and take them out when not. So we form a cluster to service this task. With X number of computers and, depending upon the workload, that many numbers of computers will operate to service the task. As the workload increases, more computers in the clusters will be made operational and, when not needed, will be shut down to save resources. This is called load balancing. This ensures that the task is being serviced properly with no undue stress given to a particular server or set of servers. Whenever a computer or a set of computers get utilized more than a particular set percentage, immediately more computers are brought into use, and the extra load is transferred to these newly introduced computers. Thus, workload is maintained across this cluster. As soon as the workload decreases, unrequired computers are automatically shut down or put into hibernate state. 2. Grid computing. Grid computing is a federation of computer resources from multiple administrative domains to reach a common goal. It is a distributed system with non-interactive workloads involving a large number of files. What distinguishes it from cluster computing is that they are more loosely coupled, have wider dissimilar elements or constituents, and are geographically dispersed. A single grid is normally used for a variety of different purposes. They are often constructed with the aid of general-purpose grid software libraries, known as middleware. The best example of grid computing is that of SETI, Search for Extraterrestrial Intelligence. This organization uses telescopes and other tools to scan the sky for radio frequency sounds over a wide range. These scans are converted into files for analysis. These files are distributed to individuals who voluntarily sign up with the organization for analysis. This is done through a software installed on volunteers' computer. This software scans the files and reports the data back to SETI. Once the file is complete, the software will download another file and continue its analysis. Normally, the software uses the hardware resources of the computer when they are not in use by the user or are idle. So if we look at this situation, we have a lot of computers from different administrative domains with different components and are geographically dispersed. The main task for these computers also varies as per their users. However, this creates a virtual supercomputer for SETI for their file analysis, amassing huge computational strength. 3. Utility computing. Utility computing is the packaging of computer resources such as computation, storage, and services as a metered service. This model gives you the advantage of low or no initial cost to create computer infrastructure. Instead, you rent all your requirements from a provider. IBM, HP, and Microsoft were early leaders in the new field of utility computing, with their business units and researchers working on the architecture, payment, and development challenges of the new computing model. Google, Amazon, and others started to take the lead in 2008, as they established their own utility services for computing, storage, and applications. Utility computing can support grid computing, which has the characteristic of very large computations or sudden peaks in demand which are supported via a large number of computers. Utility computing can be at best compared to services like electricity as a metered service, gas as a metered service, etc., which we use on a daily basis. This model is based on the same principle of us getting computing resources as a service as well. Thus, we will not have to invest in buying computers. Instead, we could rent the resources required and upgrade and downgrade as per our requirements. This same model has been implemented in cloud computing as infrastructure as a service. 4. Virtualization. In computing, virtualization is the creation of a virtual rather than actual version of something, such as a hardware platform, operating system, storage device, or network resources. We create a total abstraction of the underlying physical system and create a complete virtual system in which the guest operating systems can execute. We can hence create multiple instances of a virtual system on a single computer and implement them over the network. This also frees us from buying multiple systems and creating them over a single system, saving us from multiple hardware and maintenance costs. Virtualization is an integral part of cloud computing. If we take out virtualization from the cloud, we are looking at nothing but grid computing. We shall look into this concept later in our course. The graph shows us the trends of various computing platforms over a period of time. The time period is from 2004 to 2008, and the platforms being mapped are distributed computing, grid computing, utility computing, and cloud computing. As we can see from the graph, grid and distributed computing shows a decline in popularity and usage from well before 2004, and now are almost extinct. However, legacy systems and softwares might still use grid computing. Also, a few applications like SETI, as we have discussed earlier. We can also see from the graph that utility computing never came into fashion. It never actually gained momentum, and in India, metered computing resources were unheard of until a couple of years ago. Even today, such resources are being used by huge corporations and not by home users. We see cloud computing emerging on the graph in 2007. However, it's been around since a lot more years. If you remember, earlier we have discussed Salesforce.com coming into force in 1999, and AWS being launched in 2002. However, cloud computing started gaining popularity around 2007, when the world woke up to cost-cutting and reducing overheads. Cloud computing offers hardware and maintenance cost reduction on a large scale, and also offers ease of use. Cloud computing has now gained momentum and has surpassed all of the previous technologies we have seen, partly because cloud computing is nothing but a repackaging of these earlier technologies. Grid to cloud evolution. We will now study how cloud computing evolved over various technologies and its path. Like we have seen earlier, we have had many platforms on which cloud was developed. We have grid computing, utility computing, software as a service, SaaS, and then cloud computing. Let's go through a small overview of what is grid computing, just to jog our memory. Grid computing is a federation of computer resources from multiple administrative domains to reach a common goal. It is a distributed system with non-interactive workloads involving a large number of files. We have also seen an example of grid computing, viz. SETI. We used grid computing for a task that requires huge computational power, for example, research, etc. This was made mainstream by Global Alliance. Utility computing is where we offer computer resources such as computation, storage, and services as a metered service. This saves us huge money on infrastructure investment, and we only pay rent for the services used. This service has never picked up until now, but it's still in its infancy stage. This has been in existence since the 60s, but was not used due to insufficient bandwidth. Was rediscovered in the 90s, but again never really took off. Software as a service, SaaS. This is where a provider licenses an application to customers for use as a service on demand. This service gained momentum since 2001, but again has been in existence since the advent of the Internet. The most common example for this is your web-based email. You use your browser to navigate to the website, which gives us an interface to interact with their server and database. After logging in, we see our email and attachments, which are in reality being stored on their server. So effectively, we are using a web-based software given to us by the service provider to interact with their servers and view our data stored with them. Other examples of SaaS would be Google Maps, Picasso, Hotmail, Yahoo services, Facebook, etc. From this, you will understand that we have been using these services for ages. Cloud computing. This is next-generation internet computing. This is where anything and everything will be accessible to anyone from anywhere. Internet is a must for cloud computing. Without internet, cloud will not work. Let me say internet is the core essential of a cloud infrastructure for it to even function. Let us look at how cloud has evolved from various technologies. The underlying concept of a cloud is of utility computing. If we remember, utility computing is giving computing resources as a metered service. This is known as IaaS, Infrastructure as a Service. This infrastructure can also give you many virtual machines with varied hardware or similar hardware for use in many or a single track, thus utilizing the concept of grid computing. We have already seen SaaS, software as a service, which is also a concept in cloud computing. We will be going through these concepts in detail later in the course. Examples and studying Amazon Web Services model. Cloud computing based examples. Amazon EC2 Elastic Cloud Compute. S3 Simple Storage Service. Both these services can be classified under Infrastructure as a Service, IaaS. We will be studying the Amazon Web Services, AWS model. Google's App Engine. The engine itself is a platform as a service, PaaS, but the applications hosted by the engine come under software as a service, SaaS, as they are applications used on demand by the consumer. Microsoft, Windows Azure, Microsoft SQL services, Microsoft .NET services, Live services, Microsoft SharePoint services, and Microsoft Dynamics CRM services. Let us now look at the services offered by AWS, especially the EC2. Amazon EC2 provides a number of powerful features for building scalable, failure-resistant enterprise-class applications, including Amazon Elastic Block Store, EBS, offers persistent storage for Amazon EC2 instances. Amazon EBS volumes provide off-instance storage that persist independently from the life of an instance. Amazon EBS volumes are highly available, highly reliable volumes that can be leveraged as an Amazon EC2 instance's boot partition or attached to a running Amazon EC2 instance as a standard block device. When used as a boot partition, Amazon EC2 instances can be stopped and subsequently restarted, enabling you to only pay for the storage resources used while maintaining your instance state. Amazon EBS volumes offer greatly improved durability over local Amazon EC2 instance stores, as Amazon EBS volumes are automatically replicated on the back end in a single availability zone. For those wanting even more durability, Amazon EBS provides the ability to create point-in-time consistent snapshots of your volumes that are then stored in Amazon S3 and automatically replicated across multiple availability zones. These snapshots can be used as the starting point for new Amazon EBS volumes and can protect your data for a long-term durability. You can also easily share these snapshots with co-workers and other AWS developers. See Amazon Elastic Block Store for more details on this feature. Multiple locations. Amazon EC2 provides the ability to place instances in multiple locations. Amazon EC2 locations are composed of regions and availability zones. Availability zones are distinct locations that are engineered to be insulated from failures in other availability zones and provide inexpensive, low-latency network connectivity to other availability zones in the same region. By launching instances in separate availability zones, you can protect your applications from failure of a single location. Regions consist of one or more availability zones, are geographically dispersed, and will be in separate geographic areas or countries. The Amazon EC2 Service Level Agreement commitment is 99.95% availability for each Amazon EC2 region. Amazon EC2 is currently available in 8 regions: US East, North Virginia, US West, Oregon, US West, Northern California, EU, Ireland, Asia Pacific, Singapore, Asia Pacific, Tokyo, South America, Sao Paulo, and AWS GovCloud. Elastic IP addresses. Elastic IP addresses are static IP addresses designed for dynamic cloud computing. An elastic IP address is associated with your account, not a particular instance, and you control that address until you choose to explicitly release it. Unlike traditional static IP addresses, however, elastic IP addresses allow you to mask instance or availability zone failures by programmatically remapping your public IP addresses to any instance in your account, rather than waiting on a data technician to reconfigure or replace your host, or waiting for the DNS to propagate to all of your customers. Amazon EC2 enables you to engineer around problems with your instance or software by quickly remapping your elastic IP address to a replacement instance. Amazon Virtual Private Cloud. Amazon VPC is a secure and seamless bridge between a computer's existing IT infrastructure and AWS cloud. Amazon VPC enables enterprises to connect their existing infrastructure to a set of isolated AWS compute resources via a virtual private network (VPN) connection, and to extend their existing management capabilities such as security services, firewalls, and intrusion detection systems to include their AWS resources. Amazon Cloudwatch. Amazon Cloudwatch is a web service that provides monitoring for AWS cloud resources and applications. Starting with Amazon EC2, it provides you with visibility into resource utilization, operational performance, and overall demand patterns, including metrics such as CPU utilization, disk reads and writes, and network traffic. You can get statistics, view graphs, and set alarms for your metric data. To use Amazon Cloudwatch, simply select the Amazon EC2 instances that you would like to monitor. You can also supply your business or application metric data. Amazon Cloudwatch will be aggregating and storing monitoring data that can be accessed using web service APIs or command line tools. Auto-scaling. Auto-scaling allows you to automatically scale your Amazon EC2 capacity up or down according to conditions you define. With auto-scaling, you can ensure that the number of Amazon EC2 instances you're using scales up seamlessly during demand spikes to maintain performance, and scales down automatically during demand lulls to minimize costs. Auto-scaling is particularly well suited for applications that experience hourly, daily, or weekly variability in usage. Auto-scaling is enabled by Amazon Cloudwatch and available at no additional charge beyond Amazon Cloudwatch fees. Elastic Load Balancing. Elastic Load Balancing automatically distributes incoming application traffic across multiple Amazon EC2 instances. It enables you to achieve even greater fault tolerance in your applications, seamlessly providing the amount of load balancing capacity needed in response to incoming application traffic. Elastic Load Balancing detects unhealthy instances within a pool and automatically reroutes traffic to healthy instances until the unhealthy instances have been restored. You can enable elastic load balancing within a single availability zone or across multiple zones for even more consistent application performance. Amazon Cloudwatch can be used to capture a specific elastic load balancer's operational metrics, such as request count and request latency, at no additional cost beyond elastic load balancing fees. High Performance Computing HPC clusters. Customers with complex computational workloads, such as tightly coupled parallel processes, or with applications sensitive to network performance, can achieve the same high compute and network performance provided by customer-built infrastructure, while benefiting from the elasticity, flexibility, and cost advantages of Amazon EC2. Cluster compute and cluster GPU instances have been specifically engineered to provide high-performance network capability and can be programmatically launched into clusters, allowing applications to get the low-latency network performance required for tightly coupled node-to-node communication. Cluster compute and cluster GPU instances also provide significantly increased network throughout, making them well-suited for customer applications that need to perform network-intensive operations. Learn more about cluster compute and cluster GPU instances, as well as other AWS services that can be used for HPC applications. VM Import. VM Import enables you to easily import virtual machine images from your existing environment to Amazon EC2 instances. VM Import allows you to leverage your existing investments in virtual machines that you have built to meet your IT security, configuration management, and compliance requirements by seamlessly bringing those virtual machines into Amazon EC2 as ready-to-use instances. This offering is available at no additional charge beyond standard usage charges for Amazon EC2 and Amazon S3. AWS Marketplace is an online store that helps you find, buy, and quickly deploy software that runs on AWS. You can use AWS Marketplace one-click deployment to quickly launch pre-configured software and be charged for what you use by the hour or month. AWS handles billing and payments, and software charges appear on your AWS. Amazon Cloud users. New York Times. NYT needed to convert 15 million scanned articles to PDF files. It would have taken a huge amount of time if they would have decided to do it using their own infrastructure, let alone the time it would have taken a lot of their hardware and network resources were they to do it in-house, which would also have affected their daily work. What they did was directly log into the Amazon cloud using their credit card. They did not have to contact Amazon for any requirements and create an account. They deployed 100 Linux computers using the hardware and software resources offered by Amazon, and in a span of 24 hours transferred all that data, which totaled to 4 TB, to use PDFs using EC2 and S3. It would have taken months if they decided to utilize their own resources. Thus, not only was it cost-effective for them, it saved a lot of time without creating a hindrance on their existing network. At the end of the exercise, they deleted the 100 Linux machines they had created, and thus only had to pay for the resources consumed for their entire exercise. NASDAQs. Everyone knows NASDAQs and the voluminous data they go through every day. They have to deal with hundreds and thousands of scripts on a daily basis and give second-to-second updates daily. There are millions of files showing price changes of entities over a 10-minute segment. Storing all that data on their hardware would require a humongous investment in computer resources, also resulting in a lot of maintenance costs. So they used the S3 services offered by AWS for storage, integrated that storage in their infrastructure, and used S3 to host all that data while being in sync at all times. They also created a lightweight Adobe Air application, using which the users were able to view the required data. These two examples show us to what extent can a cloud infrastructure help us. A businessman no longer will have to invest in infrastructure and maintain a team of specialists to service it. He can now easily create everything on the cloud. Let the provider worry about the infrastructure, and he can focus entirely on his own business. All he's doing here is outsourcing his IT needs. IBM Google Cloud. Example 2. A new IBM Google initiative aims to provide computer science students with a complete suite of open source based development tools, so they can gain the advanced programming skills necessary to innovate and address the challenges of this computing model, which uses many computers networked together through open standards and thereby drive the Internet's next phase of growth. The companies will provide hardware, software, and services to augment university curricula and expand research horizons, while lowering the financial and logistical barriers for the academic community to explore Internet-scale computing. IBM and Google have already dedicated a large cluster of several hundred computers for this program, which is planned to grow to a few thousand servers over time. Using this virtual IT lab, students will learn how to develop systems and write massively parallel applications that take full advantage of the distributed computing paradigm rather than the conventional one server, one application model. The architecture used in this model will be open source to keep costs under control. Linux hosts with Apache Hadoop file system will be used with the Xen virtualization. These are existing technologies and hence will be compatible with almost all systems.